So today, let's dive into a framework that could seriously shake up how we do reinforced concrete design. Now, I want you to imagine an AI that isn't here to replace you, the engineer, but instead acts like this incredibly powerful, tireless assistant. I'm talking about one that can take a project all the way from the first concept to fully optimized, code-compliant construction docs, and do it in a tiny fraction of the time.
So let's just get right to the big question, the elephant in the room. Could an AI really, truly handle the entire structural design process? From that very first flexural calculation all the way to a final, perfectly annotated set of CAD drawings. Now I know, it sounds a little bit like science fiction, but the framework we're about to walk through shows how this is actually becoming a reality.
All right, here's how we're going to break this down. First up, we'll look at how you can actually teach an AI the fundamental principles of engineering. Then, we'll see how a bunch of different AI models can work together in a slick digital workflow. And finally, we'll tie it all together, watching it go from an optimized design straight through to finished drawings.
Okay, let's kick things off with Section 1, Teaching an AI to Engineer. Because you have to remember, before an AI can design a single thing, it has to go to school, just like every single one of us did. But its textbook is a little different. For any AI tool to be worth its salt, for us to trust it, it needs a source of ground truth. And in our world, in structural engineering, that is the ACI 318 code. So the first absolutely critical step is translating this code with all its complex rules and nuances into a format that a machine can actually read and understand. This isn't just typing things in, it's a really deep process called knowledge engineering.
So how is that knowledge actually engineered? Well, it's broken down by discipline, just how you'd expect. For flexural design, the AI learns everything from strain compatibility all the way to generating PM interaction diagrams for columns. For shear, it codifies all the logic behind concrete capacity versus the steel you need. For torsion, it learns to model that complex interaction using the space truss analogy. And, so importantly, it goes way beyond just pure strength to learn all the rules for serviceability. We're talking deflection control, crack control, and all those nitty-gritty detailing requirements.
The result of all that hard work is this absolutely massive, high-fidelity dataset. Just think about it for a second. Thousands upon thousands of input scenarios, every possible combination of span, load, and material are mapped to a perfectly code-compliant solution. This dataset, it basically becomes the AI's entire universe of engineering experience.
But you can't just dump all that data into the model at once. You have to be smart about it. The dataset gets partitioned using a pretty standard machine learning approach. A big chunk, 80%, is used for the initial training. That's where the model learns all the patterns. Then, two smaller, separate 10% slices are held back for validation and testing.
And this is exactly why that partitioning is so critical. It prevents a huge problem called overfitting, which is basically where the AI just memorizes the training data instead of learning from it. By using a separate validation set, we force it to generalize, to actually learn the underlying principles of ACI 318. It learns how to think like an engineer, not just how to copy and paste answers.
Okay, let's move on to Section 2. So we have these specialized models, right? They're trained on first principles. The next big question is, how do we get them all to work together? This is where we get into the digital design workflow and the art of orchestrating these models.
So I want you to meet the project manager, the master AI. It's really important to understand this isn't some single, all-knowing artificial brain. It's much better to think of it as a project orchestrator, kind of like a conductor for an orchestra that intelligently manages all the specialized models within a modular system. So what does this orchestrator actually do? Well, it's the main interface for you, the human engineer. It takes your high-level project inputs, and from there, it knows exactly which specialized model to call up and in what order. It manages all the data flowing between them, and it runs the really complex routines, like the optimization loops we're about to talk about. And having this kind of orchestration leads to this just dramatic shift in efficiency, especially when it comes to generating CAD. I mean, think about it. Manually drafting sections takes hours. Consistency can be all over the place, and we all know revisions are incredibly tedious. The AI, it can translate that design output into a drawing in seconds, with perfect consistency every time. And revisions, they become pretty much instant.
And that brings us perfectly to Section 3, from optimized design to drawings. This is where we get to see the entire system fire on all cylinders to achieve that true end-to-end automation.
You see, a system like this doesn't just find a design that works. No, it hunts for the optimal one. The whole process kicks off with the engineer defining a goal, maybe something like minimizing construction costs or material weight. The AI then just starts iterating, proposing designs, checking them against the code,
refining its approach over and over until it finally converges on the best possible solution for that goal.
And the speed is it's staggering. This loop can repeat hundreds, even thousands of times in just a few seconds. It's an intelligent search through this huge space of possible designs to find the one that isn't just good enough, but is genuinely optimized based on the engineer's specific goals.
So, at the end of this whole automated workflow, what do you actually get? What's the final package? Well, you get a complete and totally consistent set of initial construction documents. We're talking a full column layout and schedule, a beam framing plan, detailed cross-sections for every single unique member with rebar callouts, and full beam and column elevations showing all the reinforcement profiles, the whole shebang.
And that really brings us to the ultimate takeaway here. This is not about making engineers obsolete. Not at all. It's about transforming our role. By taking away that soul-crushing burden of repetitive calculations and tedious drafting, it frees us up to focus on what we really do best: high-level validation, understanding complex system behavior, and coming up with truly innovative design solutions.
So, I'll just leave you with this one thought to chew on. What new possibilities could you explore? What truly complex problems could you finally have the time to solve if you never had to draft another beam schedule again?